All right, everyone, let's go ahead and get started here. So actually, before I begin uh, jumping back into the computer methods for analysis section, um, I thought I might comment on a couple of problems on the homework 6 that you have. Let me see if I can pull that up. So one of the problems, I think problem 3 on your homework, um, problem 3 on your homework maybe looks like this. Pinned on one end and roller on the other. Um, and we have some load here. And the problem asks you to make use of symmetry to try to reduce the number of excuse me, number of redundant unknowns, and then be able to solve it. So before I do that, let me ask you, what is the degree of redundancy of this system? 2, right? If I take off 2 of those diagonals, now it becomes a redundant, now it becomes a determinate truss. So to make use of symmetry and to be able to solve only half the truss, or half a structure really, how have we tried to do that in the past, or at least in the examples that I showed you in class? How did we make use of symmetry to try to figure out what half system we should be solving? Go ahead, Drew. Yep, in the class examples, yes. How did we do that in the class examples? Okay, so we find the axis of symmetry, which is usually down the middle. In this case also it's down the middle. And then we find appropriate boundary conditions. How did we find appropriate boundary conditions? Say it again. Yes, for beams and frame problems, we were looking at whether the slope was 0 or the displacement was 0 at the axis of symmetry. So for example, if we go back to this, for example, this structure, we said that if we wanted to solve this half of the system, then we would need to have a fixed end at this point to make sure that the slope and the displacement both are 0, and at this point only a roller, so that it can have some non-zero slope here. But effectively what we are trying to mimic the behavior of the full system by applying the correct boundary conditions to the half system. Okay, and how do we determine that? We draw the deflected shape of this system. So that's exactly what we are going to do here as well. What would be the deflected shape of this truss? What do you think would be the deflected shape of this truss? So, well, we can start drawing that. It would go down somewhat like that. It might go something there. It might do, and actually, it might do something like that. And then the diagonals would be connected as usual. I'm not sure if that's too clear, but there is, you can expect that the deflected shape would this leg would kind of rotate in. This would also rotate the other way. These two bottom chords would kind of form an angle here. Now, is this deflected shape also something that can be achieved? Can I solve this problem with a half a truss? So if I were to try to solve the same problem with this truss, what would be the boundary conditions I would need to make sure that the deflected shape of this truss matches the deflected shape of half a truss here? We want to keep this edge vertical, right? And we also want it to be able to go down, right? So what we would want, both vertical rollers, and we want this. Now this point on the left side here is a pin. If I make this a pin and this is a vertical roller, that becomes an over constrained truss. Immediately it would become back to degree of redundancy 2. And it would also constrain the truss more than what we should. You can see that since this right end is a roller, when I apply the load, this bottom chord members are able to breathe and extend. So in order to simulate that, I would do a horizontal roller here, and for this structure now, I would get a deflected shape that would kind of look like that. So this deflected shape and this deflected shape should be the same. Aaron?
Could you explain again why you couldn't use the pin?
Okay, sure. So if instead of this roller, if I had a pin, then first of all, there are 2 reactions here, 2 reactions here, 4 reactions total. And there are 6 members, so total number of unknowns is 10. You have only 8 nodes, 8 equations, 4 nodes, so 8 equations. So you're back to a redundancy of 2. And if you were to do a pin here, then this end would not be able to extend to the left, right? So even though this end does not extend to the left, this end on the right does extend to the right. In order to allow the structure to breathe, quote unquote, breathe at the bottom, I would need to remove that pin and place a roller here. So when I solve this system, now this system has 3 reactions, 6 members, 9 unknowns, 8 equations, so redundancy is 1. But you would still have to figure out what you need to do with the vertical member out here. You cannot just choose the same properties as the vertical member out here. Okay. And I would like you all to think a little bit about whether the vertical member here, although, did I ask you for displacements for any of those cases for the truss member? Okay. Yeah, I think for displacements you would need the properties of the E and A properties of the members. But in this case, you would have to think whether you should use the same properties as the original truss, or half, or twice, or what. Okay. Questions? Okay, so for symmetry problems, what you need to do, of course, is always that uh, you need to figure out what would be the deflected shape of the entire structure and how you can make use of symmetry to solve half the structure by modifying the boundary conditions. Your entire objective is always to try to mimic the structure, to mimic the response of half the structure so that you can reflect it or replicate it to get the response of the full structure. So in this case, I'm taking, I figured out what the response of this full truss would be, and looking at the response of half the truss, I've tried to come up with boundary conditions that would mimic the same response. Does it make sense? No? Well, go ahead if you have questions. I'm here to answer them.
With the actual deflection at that middle point at the bottom be equal to the deflection of the left one instead of no, wait. Oh, okay, never mind.
Let me see if I can pull up a better picture. Was it this one?
So if we do it this method, let's say we're looking for the horizontal deflection at E, and then the horizontal deflection at E would then be the horizontal deflection at D from the half that we pressed, the bottom. Yeah.
That's right.
So we just have to relate it in terms of the
right.
result.
So I think what's important to realize here is that if the displacement so I won't draw the cross members. If the displacement of those truss pieces look like this, then you can see that point F moved to the right by some amount, and point E would have likely moved to the right uh, by about half of that, but not necessarily always half. But it is true that what you want is to simulate this part of the truss. What you are doing is you are making sure that these 2 points B and E are able to move vertically, and in order for the bottom member to have the same level of forces um, as the original truss, you would have to include a roller at the bottom at D, because you want it to be able to move out a little bit, um, to simulate the exact conditions that are there in the original truss. So anyway, this is a point that I think will require some thought on your part, and but it's so think about it. If you have more questions, I'm sure we can answer them in our office hours or in the discussion forum, unless there are some other burning questions right now. Okay, all right. So let's move on, and let's jump back into the topic that we had started last time. This topic on computer methods for structure analysis, and I pointed out the need for this. If you're not already convinced by doing homework 5 and possibly homework 6, you do not want to solve these problems by hand always. It's very cumbersome, right? So we want to be able to make use of computer programs that automate the process that we do by hand. Uh, for most of the problems that we solve in structure analysis, there is a very well laid out sequence of steps that you follow. And if you can automate that process of sequence of steps, then the computer will do all of that for you. But a couple of things that I pointed out last time for you to keep in mind. One, that you need to come up with an algorithm. And we talked about how the method of joints, the algorithm really is draw the free body diagram of all the joints, set up all the equilibrium equations, make sure that number of equations is equal to number of unknowns, and you just solve it. That's the algorithm. That algorithm can be applied to any determinate truss. Right? You give me one determinate truss, two or another different determinate truss, the algorithm does not change. Same way, the computer program that you write must not change for different structures. A lot of the times, students and sometimes practitioners also end up hard coding things into their computer program. You do not want to do that. Okay. for solving a particular problem, we always create a separate input file where we define a complete problem. We take our algorithm, apply it to the input file, and we and let the algorithm do its job. Okay. Um, and last time I had just barely started introducing some basics of programming in MATLAB, and I mentioned that if you are able to master certain basic skills in MATLAB, then you can pretty much understand and code in any programming language, not only MATLAB. Almost more than 90% of all computer programs are these two things, um, conditional statements and loops. If you follow those two things, how they work and how you can combine them and mix and match, you can understand most any code. Okay. Um, so let me first begin with understanding how MATLAB handles data. And I was telling you last time that um, that in MATLAB, pretty much everything is a matrix. Um, so let's see if I can get this straightened out. Right. So in MATLAB, there is something called a workspace, which is like MATLAB's memory, where you can create variables and then use those variables to conduct operations. So for example, when I say a equal to 10 and I hit enter, that variable is created in MATLAB's workspace. I'm not sure if you all can see. Um, Can you all read the commands back in the back that I'm entering out here? Can you see these things in the workspace as well? Essentially, what this is telling me is this workspace is the current state of MATLAB's memory. Okay. So for example, if I say B is equal to 5 and then C is equal to A times B, this just works like a calculator, right? Now, one thing I showed you last time was to create a matrix because in MATLAB, actually, even when I say A equal to 10, MATLAB treats it as a 1 cross 1 matrix. A 1 cross 1 matrix is nothing but a scalar, but in MATLAB, everything is a matrix. Okay. Um, so when I say this capital A is equal to 1, 2, 3, and semicolon to end the row, and 4, 5, and I'll start counting backwards now. 4, 3, 2, 1, and close square brackets. When I press enter, it creates a 3 cross 3 matrix. Okay. So these are just basic commands on how you can define matrices or variables in MATLAB. One thing to keep in mind here is that this small a and big A are different. So MATLAB distinguishes between the case of your variable. Small a is different from big A. Can anybody tell me how would I access, let's say, this element of the matrix A? A of A of 2 comma 3. So if I enter on the command prompt A brackets 2 comma 3, all that is saying is that go to the element row number 2 and column number 3 of the array A. Array and matrix sometimes are used interchangeably. So this is the first row right here. This is the first row, second row, and third row. So this is the second row and third column. And of course, if I enter that, we get that value 4. What happens if I enter B 2, 4, 6? If what will happen, do you think, if I enter the command B equal to square brackets 2, 4, 6? That's right. So I have already a variable in my memory called b, which is storing a scalar value 5 here. Okay. If I do that, I will immediately overwrite that value. Okay. And it will be overwritten by this vector, which is a 1 cross 3 vector. So let me ask you this. If I, how many of you are familiar with MATLAB? Okay, most of you are, but for those of you who aren't, this might be something that you might need. And for those of you who are, it might be a quick revision. What does this symbol do? Drew? Right, so it's a transpose operator, right? So this is a row vector, and if I do that, it becomes a 3 cross 1 column vector. Um, um, how about I do a backslash b? What is that? A backslash b. So let me store that in something. X is equal to a backslash b. Okay, um, and uh, a backslash b is just another way of writing a linear system of equations. So if I were to try to solve a linear system of equations, so if I have some matrix A, and maybe I'll write that as a matrix A, and I have some vector x is equal to b, and therefore I can calculate x is equal, let's see, x is equal to a inverse b, then in MATLAB I would write that as a backslash b. Okay, and we can verify that. I've already calculated x. We can verify that by saying a times x minus b, and when we enter that, we get 0 0 0. So indeed ax is equal to b. So keep in mind that this backslash operator solves systems of equations in MATLAB, and no matter what problem you are solving, at the end of the day you will be solving a system of equations, whether it's a structural analysis problem or actually most other engineering problems. um, so let's go back to this. And there's another, of course, another way to verify that indeed this is the solution to the original problem. We can do inverse, which is the command inv in MATLAB, inverse a times b, and that also gives me the same result, 4 minus 4 and 2. These are some of the basic operations that you can run by creating variables in MATLAB. So this part is no more difficult than a regular calculator, right? Now, um, in order to be able to work with bigger data sets that you can't really work on with your calculator, you would have to provide facility for the users to write, say, text, big input files or big text files that can be read into MATLAB. And one way to do that is through input output commands. And the most common input command is right here, input. So I could say something like, um, A is equal to input, and then I should enter a prompt here, enter an array. And when I do that, MATLAB, this is a command that can be included into a program. When this command is executed, MATLAB asks the user for an array, and I can enter an array something like this. Let me ask you what would be the result of this. 1 to 10, 1 colon 10. So would it be a matrix or would it be a, it would be an array of 10 cross 1 or 1 cross 10. Okay, so indeed it is an array of 1 cross 10. And the moment I did that, what happened to my previous A? It's gone. So this is the most common mistake that I see in student programs, that when students use a variable name with a single letter like small a or big A, small b, or something like that, single letter variables are prone to this type of mistake. Even if I may not have intended to overwrite my previous variable A, I've just done that. So that's why you should use very meaningful variable names. So for example, you can use A matrix is equal to, again, input, enter a matrix. And if I enter that with the same matrix that I used before, then I would chances of overwriting this mistakenly are much lesser. Okay, um, so these are some. This is a simple input command. A very simple output command is the display command, which hopefully you've all, those of you who are familiar with MATLAB, have seen before. So display is used to display the contents of a variable in the memory. So for example, I want to say display C. C is a variable in my memory. It stores the value 50. When I do that, it immediately displays the value 50. Okay, so um, all your computer programs at the end of the day would be an algorithm which feeds in some input data using one of these input commands, and it produces some output, and it displays some sort of output using some of the one of these output commands. So um, the way to kind of automate that process is by actually taking some of these commands. Let me make up a new file here. Um, where's my editor? Right. So if this is a new MATLAB file, all MATLAB programs are uh, um, are of the file type .m. Okay, so for example, this program that I had kind of initiated or very initiated earlier is called program1.m. Some of these things I've already entered in here. Now, all I've done here is taken some of the commands that I just showed you and put them in a single file, and it suddenly becomes a program. What MATLAB does is, if I click on this play button, or if I go to MATLAB's command window here, and say program 1, um, and press enter, it immediately starts executing that program. So it's asking me enter an n cross n array, and I'll get back into that. But let me show you another useful thing, um, practically the most useful thing that you'll find for programming. Um, how many of you have used the MATLAB debugger? So the debugger is a tool which allows you to follow uh, the execution of your program along with it. As MATLAB is executing your program, you can follow along the execution. Make sure that when these commands are executed, that you are getting what you expect to be getting. And if there's something going wrong, that is the most easy way to, or the most convenient way to find problems with your code. And um, trust me, when you write a few, uh, the first few programs you'll write will be full of bugs. So that's why it's called a debugger. Okay, you place what we call a breakpoint at the line, at a particular line number, and you click play, and there's this green arrow denotes what it shows is that MATLAB is waiting for me there. There was a breakpoint, so MATLAB reached the breakpoint. Now it's waiting for me there to proceed. So I'll say take one step, which is F11 here, or um, or F10. So take one step. What 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 MATLAB did right now is that it executed these commands. These commands are clear all, close all, and CLC. Clear all says clear all the variables in your memory. Swipe the memory clean. I want to start afresh with a new problem. That's a good practice to do before starting any new problem. Clear the memory. And close all means close all the any other open windows, that MATLAB related windows that are open, which is also a good practice, because there might be some other program that might have created some output. CLC simply says that clear the command window. So this is the command window. All of the commands that I had entered before now are cleared. There's nothing in my workspace either. Okay. Um, Now MATLAB is waiting for me at this command line. A is equal to input an n cross n array. So when I say execute that, MATLAB comes and asks me enter an n cross n array. Okay, so I'll enter the same array 1, 2, 3, 4, 5, 4, 3, 2, 1, and I'll just press enter. Now MATLAB asks me goes to the next line, and it's when I say execute that command, it asks me for an n cross 1 array. In this case, the value of n that I'm using is 3. It's a 3 cross 3 array. So I'll enter 246, and I'll put a transpose here because I want it to be a 3 cross 1, not a 1 cross 3 array. Is there another way to enter a 3 cross 1 array without using the transpose operator here? Okay, yeah, we can use semicolons. So I could do 2, 4, and put semicolons in between, and that would be right here, right? So now what I want to make sure is that this backslash operator does the same thing as this inverse times b, inverse a times b, that if I execute these two commands, I should get the same result. So I'll execute 1. And another good thing about MATLAB is that if you place your mouse over one of these variables, you can check its value right there, 4, -4, and 2, which is the exact same value that would be there in the workspace. And um, but hovering your mouse over the variable tells you its current value. Another point to note here is that even though MATLAB executed this command, it did not produce an output on the command window. Anybody know why that is? Was that? So actually, display command just displays whatever is in the variable. When I write this semicolon after this command, I say to MATLAB that I don't need to see the output, just compute it and store it into your memory. Okay, so the semicolon suppresses the output here, but it still executes the command and stores it in the memory. The next command I have is x2. So I had an x1 equal to a backslash b. I have an x2 equal to a inverse times b. They should both produce the same result. So when I execute, excuse me. So I'm going to press this F step again, and now I have x1 in my memory, I have x2 in my memory. They both, clearly I can see they are in the same variable. They have the same value, two different variables, and I calculated them in two different ways. They are both mathematically equivalent ways of solving a system of equations, right? But um, um, this first way of using backslash a backslash b is much faster than using inverse. Anybody know why? Why that is? Say again. Less calculations, that's true. Less calculations definitely means faster. Why is that? Anybody know why backslash is faster than inverse? How about if I asked you to solve a 3x3 system of, I gave you three equations, three variables, solve them by hand, as opposed to I gave you a 3x3 matrix and invert it by hand. What do you think would take more time? Was that? Inverse, yes. Inverse does take more time, because you uh, do need to do more operations for that. Backslash, what it does is it factorizes the matrix into a left triangular and a right triangular matrix. And then if you want to solve a vector b against that matrix, which is already factorized, then all it becomes is a simple matrix vector multiplication. So that goes much faster. But here's how, um here's the next important concept in programming called conditional statements. Um, so we use conditional statements in our programs to allow MATLAB or to allow your algorithm to do certain things based on certain conditions. So for example, in the method of joints, um, can you think of a case where you would want to use a conditional statement, or where you would do things differently if you met a certain condition? For example, if you identified a special joint which has members equal and opposite in two different directions, can you speed up the process of that calculation, right? If you have a special joint uh, where members are equal and opposite in two perpendicular directions or two opposite directions, then the forces have to be equal in them, or there are zero force members around that point. So if you detect zero force members, it speeds up your calculation, correct? So that's an example of where you would try to detect if there are any zero force members in your truss. Um, so in this particular case, I'm showing you an example um, of checking whether x1 is equal to x2. So this statement right here, by the way, before I get into these statements, there are these green lines in MATLAB. Automatically, any program is color coded. All of these green lines that are preceded by this percentage sign, this is just a comment. This is, you could write anything in there to try to document what your program is doing. So the first line here says it's an example program. This comment line here says clear the memory, ask the user for some input, and this says example conditional statement for checking if the backslash operator solves a system of equations. So the way we check conditions in MATLAB is as follows. I'm saying if x1 double equal to, so this is again a common mistake where if you want to check two variables, you don't use a single equal to sign, you use double equal to sign. If x1 double equal to x2, then I want to say that a backslash b is the same as a inverse b. If they are not the same, then I want to produce the result don't they don't produce the same result. Can anybody tell me what is the other stuff out here that I have in this conditional statement, Rebecca? Right.
So like here, two conditions that are in part of it. X1 is exactly equal to X2, or if the absolute value of X2 is like really close to zero, but like not exactly.
Okay, good. Right. So this indeed is, this single vertical line is a OR operator. Now there are two types of OR operators. There's a double vertical line also in MATLAB, but double vertical line is used for scalar values. Here, x1 and x2 are both are vector or array values, and the second condition is there only so that if the two values are very close, that they are still treated as being equal. Why do I need to do that? For example, I'll show you right here. I'll have to kill this execution, but I'll show you, maybe I'll show it to you later. Um, in MATLAB or in any computer programming application, you have only finite digits of accuracy. Okay, you have usually about 14 to 15 digits of accuracy, um, and most real numbers, you have to make some sort of a round off error. There is a round off error in the storage in memory. So for practical purposes, even though x1 and x2, they are both have, they look like they both have the same value, but even here you can see that x1 is 4 minus 4 and 2 in like integers, whereas x2 is 4.000 minus 4.000 and minus and 2.0000. And if you extend it out to further 14-15 digits, you'll see that maybe one of the last digits is not a 0, it's a 1, or 9 or something like that. So that's the reason why we have to make sure that if we are comparing two real numbers in MATLAB or in any computer programming language, we have to account for this condition, that the absolute value of the difference between those two numbers has to be less than certain tolerance. In this case, I'm using the tolerance 10 to the minus 9. So I'm saying that if two numbers match to within 10 to the minus 9, then I'm going to say they are equal. Okay. And indeed, let me ask you this: what would be the is this condition true, or which of these conditions is true? Is this condition true? Is x1 equal to x2? According to what I just showed you, this is x1, this is x2, and if I were to execute x1 equal to x2, would that be true or false? Let's check. So x1 equal to x2. And if I enter that, it tells me 0, 1, 1. What does that mean? It means that it's true for the second element of x1 and x2. It's true for the third element of x1 and x2, but it's not true for the first element of x1 and x2. And how can that be? So I'll show you why that's not the case. So format long means that I want to see all the digits of accuracy that MATLAB is storing. So when I say when I say x1, it's integers. x2, you can clearly see there is a 3.9999999 and so on. And that last digit of accuracy, loss of accuracy, is causing this condition to fail. Even though x1 and x2 for all practical purposes are equal, when you compare these two numerically stored numbers, they will not match. And that's why it's important to have this second condition. This second condition, as we will see, absolute value of this is less than 10 to the minus 9. If I execute that here, I get 1, 1, 1. They're all true for all three components. Okay. So this second condition is true. This first condition was false. The operator between them is OR, is the OR operator. So if the first condition is true or the second condition is true, do something. Do what? Display this command. If neither of them is true, then display this command. That's the simple if statement. If this condition is true, do this, else do that. That's a conditional statement that you can put anywhere in your computer program, and that allows you to make big decisions early on in your program. You can have right here. I have only one command in between the if and then and else. In general, you can have entire portions of commands or programs between those two lines. So when I execute this line, it will go to this part because this condition is indeed true, and it will display that the operations are producing the same result. So when I do that, you can see that it produced, the operations do produce the same result, and then it skipped the else part. Okay, it skipped the else part and went straight to the next line. The next line here is an example of a loop. So condition statements, that's all there is to it. If certain condition is true, do this. If that is not true, do something else. And that part is over. Now I'm going to talk about the loop part of the statement. What does a loop do? Loop is pretty much the most useful thing for as far as computers is concerned. Computers can do things repeatedly, the same thing repeatedly, very, very fast. You can put certain commands inside a loop, and they can execute that command very, very fast, multiple number of times. So in this case, for example, let's say if I were doing a method of joints, at the end of my analysis, I want to find zero force, which members were actually zero force members. So I would have to go through the solution vector of my forces and try to figure out which members are zero. Okay, that's exactly what I'm going to do here. Can anybody tell me what kind of a algorithm would I need to um, to try to find zero force member if I have a vector of internal forces in my truss, and I want to find where are the zero force members in that vector? What kind of algorithm would I need? I would be searching. I'm going to try to search for the number 0 or something close to 0 in that long vector, right? How can I do a search? Just go through each element, check whether this number is 0 or not, and if it is 0, output that. That's exactly what this loop does. So when I say for statement, for I is a variable, and I'll talk about that also. I want to check for all elements 1 to the length of x1. I want to check whether this element is 0, and if it is 0, then I want to display it. Note that there is no else part for this if. So else part is usually optional. So up here, I had an else in the if statement. Down here, I do not have any else in there. Okay. I'll talk more about this loops next time, and then I'll go through the program for solving a determinate truss also on Friday. And maybe just to show you, hang on, just to show you a sample truss program. This is a program that I will give you, and I will ask you to make modifications to it. So you do need to be able to use the program and make small modifications to it. And of course, all of this is not in your books or anywhere else. So let me actually stop debugging that and let me run this. Change folder. So I'm running this main algorithm program that does method of joins. I'll choose an input file. I'll say open that input file, and it shows me a truss. So this is a truss where there is a pin support at the left, there's a roller support here, there's a load of 50 whatever units you want to pick. There are I don't know 6 nodes and 9 elements in there. So input is okay, I'll say okay, and then in that short amount of time it has already conducted method of joins, and it has already shown me, it's showing me all the internal forces, right? I'll say okay, output looks okay, and now the final one is a deformed shape. So this program, obviously, I mean, clicking a button, you can solve most of these problems in no time. But if something goes wrong, you need to know how to fix it, and that's something that I'll expect you to do. All right. So let's stop here, and I'll see you back on Friday.